Okay, this is part 4 of the tutorial. So in the previous 3 parts, we see that C++ syntax is actually very similar to Java, right? You can direct translation. When you look at the C++ code, you know what's going on, right? But in this tutorial, we're going to introduce something that is hidden in Java, even though we talked about it, but you can't really manipulate it because Java took care of it for you in the background. In C++, it's going to be different. Okay, so I believe in tutorial 3, we create that function func.cpp, right? So we want to use that file. So let's go into Emacs func function.cpp. So this is what we did in tutorial 3. We create the point class and we use the point class to do it. Right? Okay, so what we want to do is we want to clear the main method. And just start with the empty main method. In there, we want to start a int a equals to 5. I think if you took 124 with me last semester, I feel like you know where this is going, right? Int a equals to 5. All right, so in C++, there is this operator star. This means it's a pointer. So a pointer is memory address to a variable. So in Java, that is completely hidden from you, right? Well, first of all, for primitive type in Java, you cannot access the memory point at all. Right? In Java, that is just a value. Like if you do int a equals to 5, that's all you get. You always get 5. That's a value. You won't see the memory address. You can only see the memory address through the non-primitive type, right? But in C++, that is different. You can actually look at the memory address of a variable. So how do you do that? You use a pointer. So here we have integer a equal to 5. So we create a variable, and then that 5 goes into the memory, right? It goes into some spot in the memory. And then we can do something like this. We can do int star b equals to ampersand a. So what does that mean? Okay, so there are 2 things happening. One is we have a star. So we know star means this is a pointer. So this is going to represent a memory address. Now, what does this ampersand mean? This ampersand is a reference sign. So when you have a variable like this, variable a equal to 5, you put an ampersand in front of it. This will return the memory address of that variable. So we can print them out. So if we do cout a, end of line, and then b, end of line, like this, you can actually see that a is 5, but b is going to be a memory address. So let's save and quit, and then let's do g++ function.cpp -o. All that, let's run it. So the first number, so we print a first, that's 5, and then b is the memory address of that 5. So you can actually see the memory address. And this is how you do it. You do so int a, meaning we create a variable called a with value 5. If you do int star b, it means we're creating a pointer variable. Where does that pointer variable point to? It points to an integer pointer. Memory address we get from using the ampersand a to get the memory address. Right? Now, if we don't do this, if we do we do int c equals to a, what happens? If we do c is a, then what happens is c is just 5, right? Because we are simply just copying the value. But if we do something like this, star b goes to 6. Let's see what happens. See what happens, right? So now we don't have the c anymore, so let's delete the c. If I do star b equal to 6, let's save, quit, file, run, and then we get 6. See? A is 6 now. Instead of 5, A is 6. Why is that? Why is A 6? Is it magic? No, it's not magic. There's no magic, right? So, thing is, why is A 6? Well, we create a variable, A equal to 5, right? And then we say, okay, B is going to be a memory pointer pointing to A. So essentially, B points to the same memory address as A. And then if I do star B equal to 6, so we're saying at that pointer location, put 6 in there. So what does that do? If B points to the same location as A, then we do star B. Basically, we're saying the pointer, the memory address that we're pointed to, we're assigning a 6 to it. That means we're overwriting A, right? We're overwriting A. Here's the difference. So here's the difference. If we have pointer pointing to the memory address of A, and then if we have C equals to the value of A, and we set the RB, so the pointed location of B, we assign a value of 6. See what's going to happen. Small change there. Let's see what's going to happen. Now we have 6 memory address and 5, right? So basically, because B points to the memory location of A, so when we assign a value to B, A is changed. But C simply copy the value 5 over. So C and A have 2 different memory addresses. Okay, so if you want to prove, I can show it to you. Do %A, right? Because ampersand gives the memory address of A, and I can show %C. See what this look like? Okay, different. Well, A and B are the same, but A and C are different. So it went from 3.8 to 3C, right? They're actually next to each other, right? Because one int is 4 bytes, so it goes to C, right? Because 8, 9, and 11, so A, B, C, right? So start from C, right? 4 bytes, right? Because you start from 38, so 38, 39, 3A, 3B, those are all A. And then 3C, starting 3C, you get to C, right? So those are actually 2 integers that's next to each other in the memory. So that's the difference between Java and C++, is that you can directly access memories like this, right? So that's the pointer stuff. So to declare a pointer, you do star B, and then to get the memory address of a variable, you do the %, of a variable, and then you can kind of depointer again, right? You can do star B, you can kind of depointer again. I want the value stored in that location, and I want to overwrite that with the value 6. So this is kind of like D pointer. You create a pointer here, you D pointer here, you want to put a value 6 in there. And then because B and A are both referring to the same thing, so you end up with A becoming 6 as well. Really cool stuff. Now let's look at something more interesting. So let's delete all the C stuff, right? So do you ever wonder what happens if I do this? What happens if I do B equals to 6? Let's see what happens. Let's first run it. I don't think anything's going to happen. Never mind. Yeah, so invalid conversion. Okay. So we cannot even do B equal to 6. We do B plus plus. We can do B plus plus, obviously. So we cannot do B equal to 6 because we are converting from int. So this is int to int star, right? To an integer pointer, right? We're converting from a value to a memory address that is not allowed. So that is error, but we can do B plus plus. Let's see what happens if we do B plus plus. Nothing happens. Okay. What if I do this? What if after I do B plus plus, I do star B equal to 6? Let's see what happens. I'm trying to break it, basically. Something happened. B becomes 00006. Can I actually print out star B? Hold on. Yeah, so, okay, so it's okay to print out the location of B, but then we get segmentation fault. So segmentation fault means that you are accessing a memory that you are not allowed to access to. So what's happening over here is basically when we do B plus plus, so what does it mean if we do B plus plus? So let's do C out B and L. Then we do B plus plus and then C out B and L here. And then we're going to do C out or B and L. So it's going to give segmentation fault, but it's okay because we can look at the 2B up there. I'll run. All right, so basically first we assign the memory address of A to B, right? So basically what's happening here is first this line showing this is the memory address of int A, which is a valid address. So when you have a valid address because you declared integer A is stored at this location, that is a valid address. But when you do B plus plus, what happens is you moved beyond that valid address. You move to an address that is now being declared, right? We don't even know if it belongs to the same program anymore. Like if you do enough plus plus, you can actually crash other code. Like what do I mean? I mean like if you do for int I equals 0, I smaller than, you do it like this, right? Like B will just keep going up. B will keep go up. We go. B will keep go up. See, instead of 2 something something, now we go up to 6 something something something. Right? So B will keep go up. Now, this memory block is not even guaranteed to be in the same program. Right? You might be infringing on some other program. So when you are trying to access the value in there, because this is no longer a valid address, when you are trying to do some thing like this, assign some value, then access the value, then C++ are going to say, hey, that's not your memory there. You cannot use that memory. That's how you get segmentation fault. If you see segmentation fault, that means that there's something wrong with your memory. So in C++, you can modify almost everything, right? You can manipulate memories like this, right? Like in Java, this is unheard of, right? Once you have a primitive type, you don't know where that is stored. You cannot access the memory address. You cannot increment the memory address to access somewhere else. In C++, you can do it. Even though even if you do it wrong, you're going to get segmentation fault. You can still do it in the code, which is really cool, right? Okay, so now let's look at this. Now remember in Java, we talked about ask a function passed by reference versus passed by value, right? So what I mean is we have int do some int a. In here, let's do a plus plus. Let's do C out a and L. Right, so this is going to be some description in there. Inside do some function. So in the main method, we're going to do some a, and then let's do C out a. Right? So basically we passed in a to the do something, we increment inside there, and then we do cout, we print the a inside, and then we print the a outside of the function. So if you are good in 124, you should know, well, if you took my 124 or 225, you should know that this should be, so inside should give you 6, outside should give you 5, right? So you should see 6 and 5. Return. Don't need return. Here we go. I don't need the int for return. Let's run this again. There we go. Inside do something is 6, outside is 5. So the reason for that is because we're passing in a value of integer. So whenever you call a function, another block of memory is reserved for that function, and then the argument of the function becomes a copy of the original value, right? So if we pass in the integer a, we're going to make a copy of a, so it's a different a here. I can prove it, right? So in Java, there's no way to tell, right? But in C++, we can see. And put an ampersand. A. Ampersand in front of a here. We can actually see those two. So let's compile. Let's run. See? Different. Do something is 95596C. Outside is 95594. Even though they're next to each other, there are still two different things, right? Two different variables. So this is called pass in a value. Pass in the value basically lets you. So C++ makes a copy of it. Now watch what happens here. Can I actually do this? I think I can. Start A++. Like this. I think I can do it. We'll see. We will see. So what happens here, right? Int start B equals to %A, and then let's pass in the pointer B. So instead of passing in a value int A, now we are passing in a pointer. Let's just to prevent confusion, let's call it P. And now I'm passing in pointer P. Or P, yeah. I'm passing in pointer P. So let's see if it's different now. Actually, let's see if it compiles, because I'm not sure if I can do star P++. I can. Okay, great. So now it's 6 and 6, right? Before we have 6 and 5, now it's 6, 6. So why is it 6, 6? Well, because remember pointer, we are pointing B to be the same variable, same memory address as A. We passed in that memory address as a pointer. And now they're the same thing, right? And print, I can prove it. If I print P, and here if I print %A, look, they're the same. 68cc, 68cc. So they're the same thing. Before, when you are passing in just int A, those are two different things. Now you are passing in pointer P. Now they're the same, right? Because they are pointing to the same memory address. So this is called pass in by reference. Now again, in Java, you don't do this, right? So every time when you have a non-primitive type, it's automatically you're passing in by reference. But C++, you can make this choice. It's explicit. You have to explicit say, I want to pass in the pointer. And also you can pass in a pointer to a primitive type, right? Because in Java, if you pass in a primitive type, if you want to change the A values, you have to do return. You have to actually return the value. But in C++, you don't have to, right? Because you have a pointer that enable you to do it. One more thing, okay? One more thing. You can actually, so we demonstrated using pointers for primitive types. You can also use it for objects. So you can do point A, 3, 4, right? You can do it like this. Cout A.to string. You can do it like that. You can access it like this. So in this case, we have a pointer. We have a point A. It's not a pointer. It's a point A. So we have an object A that has x, 3, and 4. Or you can do it like this. Point star B equals to new point. Let's do 5 and 6. Then we do cout B arrow dash greater than to string. Now, so you can actually create a pointer like this. Point star B equals to new point. Of course, you can also do point star C equals to %. We can do cout %A and then C. So this is another way. So this is basically I want a pointer point to this A, but here I'm creating a new point. Okay, so let me just do A and then B and then C. So let's just look at everything down here. Right? So let's save, compile. I forgot semicolon. again, pass to compile. Let's run this. There we go. So A, we get 3, 4. B, we get 5, 6. So B uses the pointer with the new point thing. And then notice, so those are the 3 values. I forgot to put a space in there, but we can kind of tell from the 0x, right? 0x is the starting point for the memory. So A, so this is A, B828. B is 0292, C, 0, so different. But C is B828, right? So C and A are the same. Oh, oops, I want to go into, yeah. So C and A are the same thing, and B is a new thing, obviously, right? Because I used it. And the syntax is different. So basically, if you don't do the pointer, you use the dot. So that's the same as Java. If you're using the pointer, you have to do the dash greater than. You have to do the arrow. The point to string, right? So that's something you have to do. Now you might wonder, what's the difference? Why? Right? What the heck? Why? Okay, so here's the difference. Now, if I do, instead of int main, let's call this void do something, do some, and then let's create a integer main down there, and we're going to call do some. Now I cannot really demonstrate this, but I can talk about this. So if you do it like this, it's pretty much the same code, right? It's the same code, right? Same effect, same outputs. The difference between doing it using this versus doing it using this, the difference is that when you do it like this, the point A will be deleted once do sum is finished. Automatically deleted, gone. If you do it like that. If you don't use pointer. So let me delete point start C. So if you don't have pointer, nothing pointing to it, once you do it like this, after you execute the do sum function, point A is gone. But point B will stick around in the memory. And you might ask, so then what? I'm done. I'm done with do sum. I don't need point B anymore, right? Can I just delete it? Well, okay. So in Java, there's something called a garbage collector. So Java basically look at all the references, all the object that's no longer needed, automatically delete them. C++ doesn't have it. So if you do point start B equals to new point, that is going to stick around and it's going to take up memory. So if you do something like this, you repeat this like a million times, it's going to get worse and worse. Your memory usage is going to get higher and higher because this point start B is going to stick around. This is why some like 40 program indie game, like you can see the memory usage goes higher and higher and higher and higher, right? It's because of this, because they used the new point, they forgot to release the memory. And then obviously, eventually, it's going to eat up all the memory in your machine and everything is going to crash, right? So, obviously, I cannot demonstrate this, right? Because this is small. This point really doesn't take up that much memory. So, I cannot demonstrate to the point where I can show that there is some significant memory difference. Also, I'm using a virtual machine, so I cannot just pull up like a task manager, right, to check the CPU usage, memory usage. It's separate, but I can talk about it, right? So basically, when you do this new point, you have to delete it once you are done, you have to do this. You have to do delete B. Release the memory if you do this. If you don't do new point, if you just simply do point A, you don't have to do this. Once do something is done, this is released. But if you do something like this, you have to manually delete B, like that, using the delete keyword. That is a big difference between C++ and Java. In C++, if you use the new thing, you have to manually delete it, basically. And you might ask, so then just don't do it, right? Just don't do it. Well, sometimes you want to do it. Sometimes you actually want this thing to stick around, right? So, for example, if you have a function like this, right? And then in there, you're going to do b set x, b get x plus 1, something like that, right? B set y, b get y plus 1, something like this. When you are passing something in back and forth, you might want to just have a pointer there so that you can pass things back and forth and around. Right? So maybe like do something in here. You want to return a point like that. Right? Now if you do point A, that thing is going to get deleted. So instead, let's do this. And then let's do increment point B. Increment point B. And then we're going to return B. Right? So then in the main, we are going to do, actually, we're going to return, okay, so this is, we're not going to return a point, we're going to return a point star. Or pointer of a point. So we have to return point star, do something. Then we're going to do point B or start B equal to do something, and then we're going to do cout B to string. So in this case, we're passing this pointer around, right, into some other functions and then return it out. So in this case, when you are passing something back and forth around, it is recommended that you use the new. And obviously, after you do this, you want to delete B because you want. So let's save. Let's see what happens. Compile. Increment point was not declared in the scope. Oh, it's the order. Ugh, I have to move this above. Yeah. Void increment point B set x B get x 1 B set. I should have just make everything public. This is too much pain. It's too much typing. Should have just made everything public. But it's the best practice. It should be private. All right. Now, there we go. Past the compiling. Let's run it. Now B becomes 6, 7. Right? It was 5, 6. We increment it. Now it becomes 6 and 7. So that's the difference between point A and then the point star B equals to new point. Right? So this one will stick around. This one create a pointer and it will stick around. You have to manually delete it. Also, this is what happens if you delete. So if I after delete, can I do this? Obviously, that's going to be wrong, right? Obviously, that is going to be wrong. See the error function. Apparently that is okay. That's really okay after I delete it? It's weird. I'm expecting to see segmentation fault. Apparently that is okay. Weird. Weird. I did not delete it. Hold on. Let me check. Delete operator C++. Yeah, that's what you do. You do delete. Using delete operator on object deallocate its memory. A program that dereference a pointer after the object is deleted. Dereference a pointer after a object is deleted. Does that mean or get why? So I'm dereferencing a pointer like this. This crash? Apparently didn't crash. What is going on? It says if it's dereferencing pointer is deleted, I have unpredicted results. That is weird. I guess this is part of the unpredicted results, right? It still works, even though it really shouldn't work. I have no idea. It really shouldn't work though. Now, what if I do this? What if I delete B inside here? What if I do that? Delete B inside do something. Now that is weird. Okay. Yeah, see, unpredicted results. Okay, yeah, so but basically it clears up the memory. And I guess if the memory is still up for grabs, it won't give you a segmentation fault. Result is unpredicted. That's interesting. All right, so this is the tutorial for pointers.